So welcome everyone. It's a great pleasure to have here Professor Luca Amendola today. Thanks a lot for accepting our invitation. Luca is a professor of theoretical physics at the University of Heidelberg. He had his PhD at the University of Rome La Sapienza. Then he was a postdoc at Fermilab, and after that astronomer at the Italian National Institute of Astrophysics. Luca is working mainly on topics related to dark energy, alternative to standard gravity, CMB, large-scale structure, and he was the leader of the Euclid Theory Working Group until 2021. Today we'll present the cosmological geometry and gravity with nonlinear clustering. Luca, please, you can start when you're ready.
Okay, great. Right, so thanks a lot for the invitation. It's really a great opportunity for me and to see how many people in the audience and friends. Very good. So yes, the title says a lot of what I want to say. I want to see how much we can test geometry and gravity using large-scale structure, in particular nonlinearity in the large-scale structure. This is a summary of work in progress since a few years with several colleagues. You still see me because I lost...
Yes.
You see me, okay, because I lost the view on my own face, which that's not a problem. Okay, so this is a list of collaborators on various topics connected to what I would like to tell you today. So cosmology, I would call it is a simple science. I don't know if you agree, but that's my view. It's simple because most of what we do in cosmology is actually related, goes around this simple equation, which, as you of course recognize, is the space-time metric, perturbed space-time metric, only the scalar part of it. And it includes, I hope you can see my pointer, it includes two potential, psi and phi, and then a scale factor, which I prefer to write in this way, making explicit the dependence on the Hubble function h, and then the curvature omega k. So the geometry of space-time at all epochs depends at first order essentially only on these three functions, h, psi, and phi, and on the parameter omega k. So I would say since 90%, I guess, of what we do in cosmology is related to this equation, I think we can really call it a relatively simple equation. Most of it can be expressed in some sense, at least in general sense, in one equation. However, it's also a science of big data and big questions. Using this expression, the space-time metric, in fact, if we are able to reconstruct it, we could answer a fundamental question, for instance, whether space is flat, how's the universe expanding, how are perturbations growing, is GR correct at all scales and epochs, and even, although it's not explicit here, whether the equivalence principle is valid at all scales and epochs. So I will try to go through some of this, probably not all of them. However, there is a key point in my talk. I would like to answer those questions without first assuming a cosmological model. And I'll try to explain what I mean in the next few slides. So you can say, well, some of these questions already got very precise answers, like we know the curvature of space to a very high precision. You know a lot about several of these parameters or functions, right? But let me give you a quick counterexample from a very recent result. You see this is one of the DAISY table of last year. There is a more recent one. And I just want to point out two things. In the first line above here, you see the value of omega k, the space curvature. Assuming lambda CDM plus curvature, you get some result. And then if you go below and see, assuming W0, WA, CDM plus omega k, you get different results. Sure, they are still compatible within the errors, I guess, but the central point is really different. And the point is that this is not just a question of statistics, it's a question of systematics. The results are bound to be different if you assume a different model. And it's even more striking if you look at the matter density. Again, I highlight two lines. You get 2.8 in this case or 3.4 in this one. That means analyzing exactly the same data, you get different results. In this case, not even really compatible to within, well, there's a tension to within a couple of sigma or something. So the results that we obtain from many of these parameters are perhaps very precise, but often they're not accurate. So we measure many of these quantities: space curvature, expansion rate, fluctuation growth, equation of state, deviation from GR. But I would say in most papers, in most work, we always assume a specific cosmology and a specific initial condition, typically lambda CDM plus standard inflation, and maybe some variant of it. That is always a standard assumption. So whenever we say we measure curvature, we measure the equation of state of the energy, we should immediately point out that this has been done assuming some specific initial conditions, so early time cosmology and a late time cosmology. Now, in this talk, I'll try to improve on both accounts, precision and accuracy, in these two ways. I try to increase accuracy by keeping assumptions as minimal as possible, and increase precision by using nonlinear scales. So I will mostly focus on model-independent measures of geometry and gravity, in particular about space curvature, cosmological excuse me, the cosmological Poisson equation, the cosmological isotropic stress, and also in recent work we answered also the question of the cosmological equivalence principle, but probably I will not have time to discuss this, but maybe I have, so I have a couple of slides on that at the end. All right, so how can we test space curvature in a model-independent way? I think the best way, maybe it's the only one. I mean, okay, there could be, I know of another possible way using strong lensing, but beside that, I think the best way would be the following. Imagine you can measure the distance, d, where there is luminosity distance, so angular diameter distance doesn't play a major role. So you can think just of the moving distance, d, but in this case, it's indeed the moving distance. And you can measure also the expansion, h, or dimensionless version, e. Then you can get omega k directly in a purely geometric way, essentially by extracting omega k from this expression here. In fact, omega k can be written as this combination of e and derivatives of d, and this statement here is completely independent of essentially of the cosmological model. Of course, we are assuming something. I will be more specific in a while, but certainly we are not assuming a power spectrum shape, and we're not assuming a particular form of the expansion of the universe, or a particular equation of state, anything like that. So the bottom line, which you find at the bottom of the slide, is that for this we need to estimate E and D in a model-independent way. Let's move on. Testing gravity. I wrote again the same space-time metric that you see a moment ago, simplified. Now there's no curvature, just for the simplicity of the argument. And you know that from this equation you can derive a Poisson equation and an isotropic stress, which in standard gravity obey these two simple relations. Standard gravity, and assuming scales small enough so that you can go into this sub-horizon limit. And this is for standard gravity. In a generic alternative to Einstein's gravity, you get two new functions, which are variously called anisotropic stress, G effective. There are various names for this, but they appear in this form. They modify the relation between the density contrast and the time potential, or they modify the relation between the two potentials. And this is what you call anisotropic stress. And again, this is valid in the sub-horizon limit, which is where essentially all the observational time are performed. So what can we do with this? Well, again, we want to test this equation without using cosmology. So we are allowed to use the equation of conservation of matter, because this is valid regardless of cosmology. It's just conservation of matter. We combine with the cosmological form of the Poisson equation, which is just the same equation as before, written in a slightly different way. And you can get from this the information that the G effective, or mu parameter, multiplied by omega matter today, can be written in terms of observable in this way, where again you see the expansion rate, and now you see a new entry, the growth rate. The growth rate f, as you know, is defined as the derivative of the density contrast, the rate of increase of the density contrast. Now, from this one, you see that if you want to measure mu, or at least mu times this factor, we need to estimate E and F. So the bottom line of this part is that we need an estimate of E and F. And of course, we need to estimate that in a way that doesn't assume a cosmology, otherwise all my argument will fail. Then finally, we can go to anisotropic stress, eta. And again, here we'd like to see how much we can do without assuming a cosmology. Now, I will maybe discuss a bit of this later on, but for the moment, I ask you to believe me. If you look at the linear power spectrum of clustering, from galaxy clustering, you realize that you can get two combination of of parameters, of information from the power spectrum. One that combines the bias B with the density contrast and the growth factor, and another one that combines again the growth factor, again the density contrast, and the growth F. And the fact that you have these two pieces of information is because you have a different angular dependence due to the redshift space distortion. Now, there are similar but different combination of quantities that you get from lensing, and it is the following one. Now you see the presence of the anisotropic stress. And the reason why there is anisotropic stress in the lensing is because lensing has to do with relativistic particles. So both parts of the space-time metric, both the space-space and the time-time, enter into the relation. So you must include that. Now you can combine in some way these three pieces of information, which are directly observables. You can combine into this P2 quantity, P3, but it's not really necessary to go into the details. What is important is that by combining this and using only the information from the conservation of matter, you can find that the anisotropic stress can be written in terms of pure observables in this way. This P2 and P3 contains A, R, and L. Actually do not contain A at all, only L and R, and E is again the expansion rate. So the bottom line now is, to measure the anisotropic stress, we need to estimate E, L, and F. Altogether, I try to show you that you can answer a lot of interesting questions in cosmology if you are able to estimate these four quantities in a model-independent way. Now, in the method I'm going to present on how to measure these four quantities, I'm not assuming any background cosmology, so I will not specify W0, WA, omega matter, anything like that. I will not assume any power spectrum shape, so I will not specify an S or anything, or the amplitude of the power spectrum. I will not specify any theory of gravity, and not even a standardization of candles, rods, or clocks, and not even a parameterization of bias growth rate. So in some sense, I still assuming a parameterization, but the parameterization is the value of those quantity at every given redshift. I'm not trying to connect one redshift with another redshift. If I know the information in one redshift bin, I use that as it is, without trying to make a parameterization to connect it with other redshifts. But I do assume things, of course. I cannot pretend, I think nobody can pretend that things can be done in a completely model-independent way. That's not science. So what I do assume is statistical isotropy, and that's a fundamental assumption. Assume that the power spectrum of clustering is intrinsically statistically isotropic, and every anisotropy that I see is because of redshift space distortion or Kopachyski. I also assume various things, which I put in gray, but all this, so the first one is fundamental. Without this, I will not be able to do anything. But the other three are actually, I can, to some extent, weaken those assumptions. So get rid of some of these assumptions. I assume a Friedman-Robertson-Walker metric, but of course, if I were to assume like an anisotropic metric, a simple one, a Bianchi one or something, I could still apply what I will tell you, except I will have to apply to different direction in the sky and then compare the results. So the methodology is still okay, but of course I will not be able to use the entire sky, but I will have to take into account possible anisotropies. I will also assume the equivalence principle for most of what I say, but at the end I will show also how you can test the equivalence principle in a similar model-independent way. And also assume, and that's very important for the simplicity, a k-independent growth rate. And again, this is not a fundamental assumption, but it simplifies a lot many calculations. So we also did a work without this assumption, but it turns out that it's much more difficult. And of course, as you can imagine, unless you have some specific dependence, then the statistics will become much poorer. So this approach is called free power, has been introduced recently. So let me go through a couple of things before I specify what really is free powers, which is actually relatively simple, but since it's kind of a bit unusual in our field, so I think I should specify a couple of things. So this expression, I guess most of you can immediately recognize, is the galaxy power spectrum as a function of redshift, of wave number, of angle, and is a function of the matter power spectrum, and then a bias factor and the redshift distortion. And K and mu themselves are a function of E and D. E is the expansion rate and D the distance because of the Kopachyski effect. So there is the bias there is the RSD there, and the Kopachyski there. And this is all essentially what we can get from linear perturbation theory, going from what you observe in space to the Fourier version of it and the power spectrum. Now let's go again and look at this expression. Again, the same, except now I wrote explicitly that k is a function of v and d, and mu is the angle between the line of sight and the k wave vector is also a function of v and d. Now the standard approach is take this expression and then parameterize as much as you can. So you write everything in terms of a few parameters, for instance, omega matter, omega baryons, excuse me, omega curvature, an amplitude sigma 8, a slope ns, and whatever, and other things. And maybe you parameterize the bias, all the parameterization you can use, the one that we often use in literature. This, of course, is bound to produce high precision results because you essentially project a large amount of data into 5, 6, 10 parameters for every redshift. So you get high precision, tighter constraints on those parameters, but low accuracy because, of course, you make a strong assumption. If tomorrow you want to change your model because you go from lambda CDM to W0 WA, you essentially have to restart from scratch. Our approach instead is to take exactly what you have, what you can read in front of you. So we take as fundamental parameters the power spectrum in wave bands, 1, 2, 3, 10, 20, depends on how much you want to go. And then we get beta or E on D, each one of them at every redshift. So every redshift has its own intrinsic parameterization, and we don't try to connect one redshift to another one through a simplified approach like writing the equation of state in some Taylor expansion, anything like that. So of course, at the end, we probably end up with low precision, weaker constraints, but high accuracy. That means minimal assumptions. And you can also say this if you prefer to be, if you really like a particular model, you can see this, our approach, as a way to compress data, which is essentially lossless. We compress the data into a set of parameters, and then you are still free later on to take these parameters, the constraints, and then project onto your preferred set of parameters. So essentially it can be seen as a first step into in the data analysis. If people could release the value, the constraints on every parameter like this, then you can still use it and project into your subset, restricted set of parameters. But I will not go this way. I will actually try to see how much we can do, what we can do about answering those fundamental questions using directly this approach. All right, so in fact, it is very simple to visualize. Instead of taking the shape of power spectrum parameterized in some way, we say, let's take the power spectrum as a free, independent parameter at every point. There are, of course, a part which you can call linear and a part you can call nonlinear, and this you will see it's actually very important for, not just important because it increases a bit the statistic, but it's really fundamental to break fundamental degeneracies. All right, so that's the free power method used essentially as few parameters, the most general parameterization you can think of. Every bin is its own parameter. Now, there are two fundamental problems with this. Take the linear power spectrum. This is the same expression as before. Now I wrote it explicitly, the growth factor. If you explicit this square here, you get 3 terms. Now, if you look intensely enough at these 3 terms, you will realize that if you fit this to the data, then you can get only 2 combinations, not 3. This combination, bias times growth times shape, and this combination, the famous beta parameter, f divided b, which means you cannot get separately f, p, and b. But if you remember, f was one of my building blocks. If I don't get f, I cannot go through my program. So I need to break this fundamental degeneracy. There is a second one, which is a bit more hidden, is in the Arco-Pachitsky. Remember, k and mu depends on distance and e again, and this is the standard Arco-Pachitsky, is nothing new here. This d, the quantity d, depends on the angular diameter distance, and just for simplicity, we divide by a reference value. That's very common. And the same for this combination in d. This is what often is called actually the Arco-Pachitsky parameter, and this sometimes is called the isotropic distortion parameter. But let me call them, all of them, Arco-Pachitsky for simplicity. Now you discover, it's not obvious, of course, from this expression, that d, this one here, is actually degenerated with p of k at the linear level. This quantity is not, but this one it is. So you cannot measure d directly from the linear power spectrum. However, you can do that with nonlinear scales. So my claim is that nonlinearity breaks both degeneracies, which means not only going nonlinear you have more modes, so you improve your statistics, but also you improve the systematics. You can break degeneracies. This plot shows relative error of some quantities, a function of Kmax. Kmax is the smallest scale at which you have to cut your theoretical power spectrum because you don't know how to go beyond unless you have n-body simulation and you trust lots of subgrid physics. All right, so this is the relative error. Now look at this number, 50. If you stop your Kmax at 0.06 or 0.1 or something, the error on D is essentially huge. 50, not percent, it's really 50 times the relative error. So it's completely swamped out. There's no information at all. But you can still measure relatively well the combination ED. As I told you, D is degenerate, ED is not. But if you improve if you extend your Kmax range, you go to smaller scales, then at some point the error on D becomes dissimilar to the error on the other parameters. That means nonlinear scales break this degeneracy. The same is for F and B. They are completely unknown if you go to relatively small Kmax, it means purely linear scales, but the degeneracy is broken when you go to high Kmax. Now, of course, there is also a tendency, you see these dotted lines, this is the tendency you would have expected just because of statistics, because the number of modes are increasing like k to minus 3 half. So that's the expected behavior. That's the expected behavior, but this is actually what you get. So the degeneracy is broken not because you had the system, you had statistics, or at least not only because of that, but fundamentally because you're adding systematic, different information from nonlinear scales. Of course, feel free to interrupt me at any time. All right, so we have to go nonlinear. No way out. Nonlinearity means that we have to complement the linear power spectrum with the so-called one loop and ultraviolet corrections. This expression is a bit more complicated. There's also a damping factor, there's also Shot noise, but this is just the standard perturbation theory. Now, this normally typically help you to extend the validity from like 50, 60, 80 megaparsec to 20 or so, which doesn't seem too much, but it's a lot because the number of K modes increases like K to the power cube, and the error goes down like K to
Can I ask a question?
Yes.
So yeah, but isn't this formula basically does assume that it only works in FLRW, this the ability to calculate this one loop and all that? I mean,
no, FLRW, I'm certainly assuming. If you refer to Einstein deceit or other things, you will see in a moment that I'm not assuming that.
okay.
FLRW, sure, I'm assuming FLRW. So I'm assuming a metric, which is FLRW at the background, and then perturbed. But the perturbation, not assuming that is built on any particular mode, as you will see in a second. Is that your question?
Yes, okay, thanks.
Yes, okay, good. Yes, absolutely. All right, in fact, that's the point. This is the standard perturbation theory. We have to get these two quantities here as much model independent as possible. Let's see how much we can do that. So first, 2 slides introduction to nonlinear perturbation theory. These are the standard conservation Euler-Poisson equation that you read in every textbook of hydrodynamics. And we want to apply this to, and of course, in Newtonian physics, and you want to apply this to cosmology. So what you do is to introduce the density contrast, adopt comoving coordinates, adopt conformal time, subtract the Hubble expansion, introduce the velocity divergence, and assume zero pressure. Once you do all this, then you get these two equations, which is the same as the one before, but written specifically for cosmology, and that includes second-order terms, these two terms there. And in order to make progress for that, you expand the two quantities, which are now delta and theta, the density contrast and the velocity divergence. You're expanding in a series, and then you're able at the end, after some relatively straightforward but complicated calculation, you get that the second order and the third order parts of delta and theta can be written in terms of the first order variables times a kernel, and all three terms of at the third order will be three first order terms and a kernel, and similarly for the velocity. So the key point here is that everything can be expressed by combination of linear Gaussian fields if you're able to calculate these kernels, F3 and G3, G2 and F2. Now, this is not something that I did myself. This I copied from a huge literature in the last 20, 30 years efforts starting in the 80s by many people. I'm sorry, I quote only a few of them. And the final result of this is that you can write down kernels like this Z2 and Z3, which include bias and redshift correction. The bias is a general form of bias, which includes other bias, which is like BG or B gamma or B2. There's been a long discussion about how many bias parameters you need. This is not based on Einstein de Sitter, it's not even based on lambda CDM. All the expressions are kind of generic. I will tell you now how generic they are. And you can obtain this essentially basing yourself on fundamental symmetry principle, like assuming equivalence principle, momentum conservations, and things like that. You can do that. Of course, the price to pay is that lot of these quantities like B, BG, B gamma, and some other quantities which are inside F2 and G2 are actually generic free functions. You cannot write them in a general way. You have to take them as they are in a completely unspecified way. So they add to our set of parameters in a free way. That's how we can go beyond the standard Einstein de Sitter assumption for nonlinear perturbation theory, which means now we have not only the shape of P, not only F, maybe even K dependent, not only E and D and whatever, but also a new set of parameters. And actually there are even 2 or 3 more, which I didn't write down here, which are essentially generalization of the bias or the UV corrections. And they're completely free new parameters, which we don't want to parameterize, don't want to specify, so we keep free at every redshift bin. Fortunately, they're only redshift dependent and not K dependent, at least in standard perturbation theory to second order. So of course now we have more modes because we go to nonlinear theory, but also more parameters, more free parameters. So it's not even obvious whether we gain anything. Fortunately, we can use an extra piece of information, which is the bispectrum. So the power spectrum is the correlation between 2 points, and the bispectrum is the correlation between 3 points. It can be written as the average of delta of wave number K1, K2, and K3 when this condition here, this triangular condition, is satisfied. Now, the nice thing about the bispectrum is that we don't need to do any more calculation of these tricky kernels, because the kernels goes into this P1 loop, and also some of the new parameters into the ultraviolet correction. But the bispectrum at 3 level only includes the same kernels that we already used, in particular this Z2, which was one of the kernels before. So we don't need to do, we need to use this, but there's no fundamental calculations to be done at this level, at the 3 level, at the 3 level in the bispectrum. So now, can we apply this technology to real thing? We did 2 things, and that's how I'm going to finish in the next few slides. The first one we applied to some data set so far, and then we did forecasts for the future. So we started applying this to the only available large-scale detailed data set available up to a few months ago, which was BOSS. And we applied this to 2 bins, one redshift 0.61 and another one. There's only 10 to 6 galaxies, so an order of magnitude less than days in Euclid, or even less. And we adopt a simplified form of free power. We didn't include bispectrum at all, and we stick to a growth factor which is K independent. And also here we simplified a lot by assuming a simplified form of the kernels, which indeed was just the Einstein de Sitter. So this, of course, is an assumption in our treatment. It's also true that people have shown that the Einstein de Sitter is a good approximation even for lambda CDM and for many other models. But we certainly are aware that this was a strong simplification, so that was just the first step, and we are already working on how to generalize this. Actually, we did generalize when we do forecasts, but for real data application, we decided to do the minimal interesting thing beyond what is usually done. So this is a typical result. I don't want to go into much detail. You can get constraints on the distance, which now we just prefer to call L, and E, and F. Directly F, please notice, this is not F sigma 8, it's directly F. If you measure F sigma 8, that's very nice, but I will not be able to use it for what I want to do. So I really need to get F. You can get F only going to nonlinear scales. We apply this to BOSS 0.38. If you compare these error bars with the one you find elsewhere, even from the same data set, of course, you will find that our confidence regions are actually larger by a factor of several, 2-3 times larger than the one you obtain by specifying the cosmology. That's totally expected. But still, this is the first application. I think is an interesting way to go. The way to go next, of course, is to make forecast. So once we have E, D, F, and not including L for now, a several redshift, what can we do? How exactly we can use them? How sensitive we can be in measuring those quantities that I mentioned earlier? So we combined boldly Daisy and Euclid into a futuristic, in what we will have in a few months from now. Combining Daisy result and Euclid, that is a forecast and not using real data now, just the expected volume, redshift, and densities from the two experiments. And we say if we can combine them in a single survey, how well we can measure things. So we did this forecast, and now we have been very general. We include everything by spectrum, all the generalized kernel, but we still keep the growth factor to be k independent, so still to go in that direction. And what we got is that you can measure the space curvature using nonlinear galaxy clustering, using this geometric formula, but obtain the E and D obtained through the nonlinear galaxy clustering. And we find that you can measure omega curvature to 0.05 or 0.06, and if you're a bit more aggressive, to 0.04, which of course again is much larger than the error from Planck, but is unique in the sense that it's almost model independent. Of course, I will never claim that we are absolutely model independent. And this, of course, this is assuming omega k is a constant. But if omega k for some reason is not a constant from redshift to redshift, then you can use the same procedure as a test of the Copernican principle. We did not do that. This would be the likelihood for various omega k independently for bin to bin. And when you combine into a single value, a single constant value, then you get this relatively tight likelihood in the middle. Then we can use this to test Poisson, and if you remember, to test Poisson we need E and F, so we have now E and F in our method. Unfortunately, you cannot fundamentally measure the G effective or mu. You always are bound to measure this multiply omega matter, and unfortunately, number 2, omega matter is not a model independent parameter, so as far as I know, as far as I can tell, there's no way to disentangle these two things in a model independent way. So, but you can take ratios of these two quantities at different redshift, and if your mu depends on redshift, which is of course modified gravity, then you will be able to tell whether it depends on redshift or not. So in that case, you get rid of omega matter. Anyway, considering these combined parameters, we find that you get error of 20% in each bin, and few percent error if you now start assuming more and more restricted things. For instance, you might say, well, let me assume mu is actually constant or follow some specific prescription, then of course you can restrict as much as you want. And just for illustration, we show what happens if mu is constant. This is again to illustrate the fact that we get general constraints, but then it's very easy up to essentially a projection if you're using Fisher matrix or a transformational variable if you use Monte Carlo to project into a more restricted parameterization. Finally, the eta, didn't spend much time on eta, because eta requires an extra ingredient, which is lensing, and we did also for a forecast for that. By the way, in this case, this relation is completely linear. We not even try to go non-linear in this context because it was a bit too complicated for now. So we did the same operation, but now there's no problem with linearity. Those degeneracies that I mentioned earlier do not refer to eta. And we get constraints on eta of the order of 20% independently in every bin, again combining Daisy and Euclid, and we only restricted to these 4 bins there. And the recent paper published by my collaborators. And again, if you prefer to have a constant eta or make more restricted assumption, then you're free to do so, and then you get, of course, better constraints. Finally, if I have time, sorry, I lost. I think I have a couple of minutes, right?
Yes.
Yes, very good. Yes, then I want to spend a couple of minutes on this last slide. So I mentioned the equivalence principle. Now, this would require, I guess, a talk on its own. But still, since it's very recent result, I'm happy to present it here. So you can also do very similar, not exactly the same, very similar model independent test of the equivalence principle. Now, equivalence principle now refer to a particular form of the equivalence principle, whether dark matter and baryons follow a different gravitational sector, where they feel different gravity. Now, if you work out what is the Euler equation for dark matter, when there is a when baryons do not follow the equivalence principle. Sorry, when baryons in dark matter, actually, for simplicity, we just assume baryons follow standard gravity, so there's no screening problem, and dark matter just follow a form of, it could be scalar tensor gravity, but we don't have to specify because we are in a sub-horizon Newtonian regime. So all it happens is that dark matter will feel a different coupling, an extra fifth force. Now, if you write down the Euler equation in this context, then you discover that you have two terms that go beyond what you have in standard gravity. A terms which modify what we call the friction, which is this theta, and a term that modifies essentially the Poisson equation, which is this gamma here. So they will be both zero in the case in which there's no violation of equivalence principle. Now, if you work out the power spectrum using this, you discover that there is a particular combination of this theta and this gamma, and also mu g. Mu g is the same g effective that I mentioned earlier. There's a particular combination which is exactly 1 when the equivalence principle is not violated and deviates from 1 in the general case. So this is the, in our view, is the fundamental combination of parameters to test. And the nice thing is that you can test this in a completely quote unquote, in a relatively model independent way, without assuming a cosmology, without assuming a power spectrum shape, without assuming a bias, and so on and so forth. And this requires, it's interesting, but again, this will require much more discussion, but in case somebody is interested, it needs to use the multi-tracer techniques. You have to divide galaxies into two classes and use this. If you don't use multi-tracer technique, you can still do this, but it becomes much harder because essentially the effect moves to higher order in the fundamental order parameters, which is essentially the scale as a function of the Hubble scale. So we are using relativistic corrections. We have to go to very large scales, and we have to use a multi-tracer technique. Otherwise, the problem becomes much harder. Anyway, it's nice that you can identify this simple combination of parameters. We measure it, we did a forecast for it, assuming since it's a multi-tracer, you have to define which bias a galaxy population and the other galaxy population follow. So there's not much information on that. So we did various cases, and typically we find that we can measure this EP to 10, 20, 30%, sometimes even a bit worse, but separately in every redshift bin. So we could be able to use this to test the equivalence principle on many redshift bin, but not soon, because we ended up with this forecast, with the forecast for DESI, Euclid, SKA. We realized that only SK2 has the amount of statistics sufficient to measure EP. DESI and Euclid, unfortunately, will not be able to do this. We really need to go to very large scales and still maintain a large density. All right, so I'm actually at the end. So let me just read through this slide. I try to show you that we can answer the question whether space is flat, measuring omega k, as the universe is expanding, measuring h and d, how perturbation is growing, measuring f, whether Poisson equation is correct at all scales and epochs. Well, all scales and epochs. At the scales and epochs that you can measure, you can observe, of course. The question is whether you can measure at all scales and epochs, and of course we can only answer this in some scales and some epochs. The same for GR, and finally also for the equivalence principle. And that's the end of my talk.
Thank you so much. Thank you for the very nice talk. Any questions? Marie-Noël?
Hello, guys. I would like to know how you could increase the relatively low precision of your method while keeping its high accuracy. Would you have to straighten your assumptions while keeping the well-physical behavior of your method?
Yeah, thanks for the question. Of course, there are several ways. One is obvious. Once you do this, then you take the results and project into a smaller set of parameters. So, I mean, we did forecast, I didn't mention, by using a simple Fisher matrix technique. That means the end of our result is a matrix. If you project this matrix into W0, WA, and whatever, you get, of course, tighter constraints. But your question is more general, whether I can improve the constraints without doing that. Then the only answer, I think, is to add more higher order moments, not just the bispectrum, but maybe trispectrum, and include maybe even going to higher order in perturbation theory, but this is very, very tricky. And also includes other probes. So, for instance, in the in most of what I said, except on eta, I did not include lensing. I didn't even include many things. Like for instance, I didn't include, you can use standard candles as tracers of structure. All of these we have shown that it helps. We did show that in linear theory, not in nonlinear ones. So there are various ways, I would say, to add more probes and to still keep model independency. But yeah, it has to be done.
But there is also the isotropy you
Okay, that
assume.
one. Very good. Well, that one, no, I mean, as I say, you could redo exactly what we did, just taking half of the sky, 10 square degrees. Of course, then the statistic will be much lower. So what I say is that if you are worried about the fundamental anisotropy of the universe, I agree with you, it's a very important question to, to discuss and to be aware of. Then the only way you can do it is, I guess, to look at the clustering in this direction, that direction, compare it. No?
Yes.
Yeah, this can be done. What I want you to say at the beginning, of course, I'm not assuming anisotropy fundamental, but if it is a large scale anisotropy, not a completely random crazy anisotropy, then you can apply the method, except you have to restrict to a smaller section of the sky.
Thanks.
Thank you. Deng?
Very nice talk. I just have at first I have one question about your formula. Can you move to the slide MKZ and the it and the P2? I mean mu and eta.
Yes. So the initial formula?
Yeah. Is that
Yes.
and in this slide, here P2 is actually depends on omega n0, right? And
Correct.
you spoke your method is independent of the background expansion. Actually, we need insert a value of omega n0.
No, because the measurable are R, L, and R. That's what you measure. That's the expression. You have it, but that's what you measure. So here, on this left-hand side, there's only observables.
Yeah.
It's because it can be written in this way that you can get eta. But I don't have to put any eta. Sorry, eta. I don't have to put any omega. That's
Okay.
different from, there's also this EG quantity. Actually, this is essentially EG. This EG quantity. If you use only the EG quantity, you need to know omega matter. But if you combine with all the rest, you don't need to.
Yeah. Is that okay? But you here omega m0 is strongly correlated with the mu, right?
Correct. But I don't need to know them.
If we want to test the GR, you must.
Then you refer to this other slide.
Yeah.
Then this slide is a different thing, and then you're totally correct. I cannot break this degeneracy unless I take ratios, and then of course I need to hope the mu depends on time, otherwise it will be constant.
Okay. I have a quick one. Do you believe this is evidence of dynamical dark energy? This is problematic.
Yeah, you mean if I believe in the DESI results, or what is your question?
Yeah. I mean, this is because DESI found a strong evidence for
Yeah, I
dark
know.
energy, and do you think it's a correct or because I think the combination is problematic. So
Yeah, I know. Then we discussed a bit over the mail. I know your point. Yeah, I'm actually. I mean, even the DESI people, frankly, if you ask them, they of course they
Yeah.
know what they're doing, I guess, and what's the problem? Everybody knows is that the degeneracy line of the confidence region of DESI points exactly towards lambda CM.
Yeah.
That's very worrying because, of course, there's no reason. So that's actually an extra coincidence. So either it's a coincidence or the degeneracy points there because that's where it wants to go, which means maybe some subset of the data are telling a different story and should be removed or improved. So, but they are well aware of this, and so I mean, I personally I'm skeptical by nature. So but yeah, but from what I can say is that also the C people are worried that there could be some hidden feature in the data that if you remove low redshift supernovae, you get a different results. If you remove a beam, they're trying to do, of course, they do a professional job of doing everything that you could. So
Yeah.
you totally have to respect what they're doing. But everybody, I think, is concerned about this. So I am too.
Okay, thank you. Very nice talk. Thank you.
Thank you. Valeria?
Yes,
Ciao,
hi,
Valeria.
thank you very
Piacere.
much, grazie for a very nice talk as usual. I have a question, actually two questions. One is on the bias parameters that you had at some point. How does it, I think in the examples that you had shown, you had marginalized, right,
Sure.
over them. So how does it change if they're also k-dependent? Is that very
Well,
much more complicated, or you would just parameterize that?
no, of
And
course.
sorry, the second one
Yeah.
is also if the two redshift that you showed, I imagine that the choice is dictated by the fact that you're using the Bose data between 0.2 and 0.7. So you picked two numbers in that range. But do you see, or have you tested this, for example, also with completely different redshift ranges, for example, even with the CMB data?
So the first question was about the bias. So in this standard perturbation theory expansion, really the various bias functions have to be only z-dependent. The idea is that the k-dependence is taken care of by the expansion itself in a different way, not in the bias. So if you follow the philosophy of the standard perturbation theory, that's really not a choice. You have to use it. That means if there is a k-dependence, essentially the k-dependence will be given by higher order terms that you are not considering because you're stopping the second order. So this is really quite a safe assumption. I don't think we are. What is important for us, of course, is the k-dependence in F. And the problem with that is that all these kernels that have been derived so far, even if when they have been generalized using symmetry principle, they always assume essentially that there's no new mass scale. That means there's no k-dependence anywhere except the one that is essentially comes directly from the Euler and the conservation equations. So if there is an extra mass scale like a Hordensky field with a mass, then that will introduce, or even neutrino mass, that will introduce, of course, a k-dependence in F. And unfortunately, there are not many results in this direction, so we are actually just now finishing a work in which we calculate the kernels, including a Hordensky k-dependence. So at that point, the problem will be not very serious because the point we will have a specific k-dependence, and then we can just add the relatively simple parameterization, but it is a parameterization justified by the Hordensky class. So will not be totally general, will not include I don't know, anything that is beyond Hordensky. But yeah, so it's possible. That, of course, will certainly reduce the statistics a bit. But if we stick with the Hordensky form, for instance, then that will not be a big problem because essentially there are only a couple of additional parameters. Now, your second question was about, yeah, of course, we use Bose. We just essentially replicated the Bose analysis that were already in the literature, except with our method because we wanted to compare. So we use exactly the same specification, the same part of the sky, the same redshift. And of course, now as soon as we have more data, we will improve it. We are working we are preparing to work on Euclid data, and we'll see. Is this your question, right, Valeria?
I was also asking if, for example, if even the CMB
CMB is another story
could be used in a completely different range.
I don't know.
Yeah.
I don't know. This is a question that I often receive and ask myself. At the moment, I couldn't find a reasonable way to apply this model-independent technique to the CMB. I mean, of course, you can say, take the CMB, take the initial power spectrum in bins, and this has been done by several people. And yeah, so you can reconstruct instead of using the power spectrum. Okay, but that will not help much for all the other parameters, not for E or D, or maybe it can, but yeah, so the answer is that actually I don't know. I tried to think about how to apply this to CMB and I couldn't find a simple, reasonable way, except the trivial one of breaking the initial power spectrum into many bins and see what happens, but this has been done already.
Thank you.
Thanks.
Thank you. And Salvatore?
Ciao Luca.
Hey, ciao, Salvatore.
Ciao. Very nice talk. I have just a very short question. When you are trying to probe the equivalence principle, is it possible with the same method to probe also the local Lorentz invariance? because this could be very nice in order to test the Schiff, the Schiff conjecture.
Yeah.
That when you are, since you are also using data that could be interesting in this perspective.
So you're taking me completely off guard. So interesting suggestion, Salvador. I'm happy to discuss with you anytime.
Okay.
The answer is that I don't know.
Okay.
So this was very specific for the EP because we came up with this particular combination, and it really is the only one that you need to measure in the power spectrum. So I don't know. I felt lucky when we found this, but maybe we are lucky twice. So yeah, that's interesting input. Thanks, Salvador.
Okay, thank you.
Thank you. Pierros?
Thank you for the nice presentation. So my question was more related to the data aspect. I was wondering why you have chosen to do the analysis on data while if you were doing that on a simulation, which is a standard practice, you know exactly the input cosmology, so you can see how accurate is your method in a more precise way.
Thanks. This is a good input as well. Of course, you're right, but we are using exactly the same kernels that everybody is using, so we're not improving that direction. So this has been done many times to use the kernel, these sophisticated improved kernels to test how well you can fit simulation. So I trust this previous result because we are not changing essentially anything in that direction. So now your question could be, why don't we take all our technology and apply it to simulations? Fine, we should actually. We are thinking of doing that. But what for? I mean, just to see. I mean, we're not testing the power spectrum because it's already been done, and not testing the spectrum. So we could do that to prove
It's to see exactly how accurate is the method in respect of a different analysis, because when you use a simulation, you know exactly the input cosmology. So when you do the measurement there, you should retrieve exactly the same cosmology. So
yeah. No, of course, you're right. Absolutely. Except as I say,
kind of like a Fisher analysis, basically, but with data.
yeah, and of course, no, you're absolutely right. And of course, we thought of doing that, although we haven't done it. But as I say, so the technical part is the kernels, and this is not new. We're using the one that is used in the literature, the most general ones. So that's not new. So this should work the same way as it's working for everybody. But yeah, you're right. Of course, we could redo this and just say how well we can recover the power spectrum from simulations. And yeah, sure, it's something we should do. I agree with you.
Okay, thanks a lot.
Thanks.
Thank you. There are also a couple of questions in the chat.
The question is whether in the Poisson equation there are terms with higher order of h dot, h double dot. Is this method you explain here could be applicable? So I guess you refer, so all these terms, all these extra terms in the Poisson equation can in principle just be called mu, no, a G effective. So I'm essentially assuming that whatever is your Poisson equation, regardless of how it's modified with respect to GR, you can always call the modification mu. And if you don't know what mu is, if you don't specify what mu is, what the G effective is, if you say it's a completely free function, then I think you can do that, and essentially you're covering all possible modifications. Remember that I say that this was valid in sub-Sand horizon regime, which means essentially if there is an extra field there, we are assuming that the clustering of this field is not important at the scale that we observe. It only modifies the fifth force, but doesn't introduce. But even that, actually, if mu is completely free, I think you can always call it mu every modification of the Poisson equation. So it should answer also your question. But let me know if my answer was not.
So I think we can thank Luca again. Thank you so much.
Thanks a lot, Eleonora. It was really kind of you to invite me. Thanks, everybody, and ciao to all my friends.
Thank you.